Hello. Our capstone project is contactless DC battery charging in an underwater environment, sponsored by General Dynamics Electric Boat. The technical directors that overviewed this project were Michael Bronner and Robert Scala. The team consists of 3 electrical engineers.
Hi, I'm Caitlin.
Hi, I'm Tim.
And I am Arthur, and we are Team Contactless DC Battery Charging. So just a little bit about General Dynamics Electric Boat. They commissioned the first U.S. Navy submarine. They are the prime contractors for the Virginia-class submarine program, and right now they are developing the Ohio replacement third-generation ballistic missile submarine.
So our project's motivation is mainly focused on how the next generation systems will be different from what is in use now. The AUVs will be more reliable with how they charge because they won't need to physically be in contact with the subs, which will increase platform flexibility and support a range of voltages in seawater conditions.
The anticipated best outcomes for the project was to develop a contactless DC charging concept model for use in an ocean environment, and to develop a prototype to support a proof of concept demonstration.
Our team was able to achieve the anticipated best outcome of our project. We developed a contactless DC charging concept model for use in ocean environments. We were then able to develop a prototype to support our concept model. We tested our prototype and it was successfully able to wirelessly transmit power. The pictures on the right show our prototype test setup. To summarize our team's key technical accomplishments towards achieving our ABO, we started with background research on three-phase AC power and AUVs. Next, we identified technologies of interest that we could use to develop the wireless power transfer system. The technologies of interest that our team identified and researched are electromagnetic induction, electric field coupling, radio frequency reception, magnetic resonance, resonant wireless power transfer, and microwave wireless power transfer.
We then created our Pew Matrix down selection. This was the tool we used to compare all of our technologies of interest and ultimately decide on which one we would end up using for our prototype. This leads me to our next accomplishment, which was our Ansys Maxwell simulations. Ansys is an FEA tool that simulates how certain technologies would work in a specific environment. More details about simulations will be mentioned later on in this presentation.
To continue with our technical accomplishments, we simulated our final system design within a simulated ocean environment on Ansys Maxwell, and then composed a prototype proposal that consists of our simulation results, the hardware parts needed, and our build and test approach.
Finally, to achieve the anticipated best outcome, our team procured the required hardware and built our prototype contactless charging system. Some of the components we used included Litz wire, which was used to make our coils, a diode bridge module, which rectified the output power, ferrite plates, which our coils are placed on top of to enhance charging efficiency, and ponding compound used to protect our coils from the seawater. We also created the environmental conditions using a fish tank filled with seawater and tested our prototype to see if it could wirelessly transmit power under the water.
This is our system block diagram. It is an overview of our wireless power transfer system, showing specifically an induction system. Next, I will be talking about my technical contributions. So my first technical contribution was to look for technologies of interest. One technology I researched was microwave wireless power transfer. Microwave wireless power transfer with a frequency wave of 300 MHz to 300 gigahertz enables power transfer from up to a few meters. The microwave wireless power transfer system consists of an energy radiating antenna and a secondary antenna, which converts the microwave power into DC power. However, we unfortunately determined that this technology isn't compatible with the underwater environment. My mission was to research the application of shielding coils. I learned that a system with shielding coils performs better because its maximum efficiency is higher compared to a system without shielding. Next, we needed to find hardware so we could put our prototype together. We also needed an environment for testing, so we ordered a fish tank and took a trip to the Narragansett beach to fill up buckets of seawater. Below is a picture of Tim and Arthur filling up our fish tank with the seawater we retrieved. I also researched the potting and molding compound MG8800. This was needed to shield the electrical components from the elements. We originally planned on using PR1547, but we shortly realized it was going to be much harder to get shipped to us in time. So I researched for an alternative, which was the MG8800. PR1547 and MG8800 are very similar. They're both two-part chemically curing polyurethane compounds that are designed for this kind of application. And I'll pass it on to Tim.
The technology of interest that I focused on was resonant inductive coupling. Resonant inductive coupling transfers power through the near-field magnetic coupling of coils. This technology's utilization of resonant coils enables it to have a more efficient power transfer over a larger separation distance when compared to traditional electromagnetic induction. This was our team's chosen technology for prototype development. However, we decided to implement an inductive charging system for the prototype instead, due to the availability of resources and time efficiency. I also worked on several finite element analysis simulations using Ansys Maxwell throughout this project. In these simulations, I tested several combinations of coil designs and ferrite geometries. I compared the different coil designs' H-field results as well as their efficiency during misalignment. I also made a resonant model simulation. The photos on the right show the results of some of these simulations. When putting together our prototype, I made the secondary coil out of Litz wire, which is a type of multi-strand wire designed to reduce skin effect at high frequencies. Even though our current design doesn't use high frequencies, we chose to use Litz wire for our prototype so that our coils could be used in a resonant inductive system in the future. I also modeled and 3D printed a test mount for our coils. This allowed us to pot the coils as well as test their efficiency easily at different separation distances. And now I'll hand it off to Arthur.
For my technical contributions, I focused my research on EM induction, which is running a current through a coil that produces a short-range magnetic field that will run an electric current through a different coil within the field. This power transfer works well in a very short range of distance. I also worked on various Ansys Maxwell simulations. Some of my simulations are shown below. For my hardware technical contributions, I focused my work on composing the primary coil of our system. I also worked with the ferrite plates for our system that helps delivers a higher charging efficiency by suppressing interference. This way, the flow of magnetic flux is retained between the two coils. I also focused on installing the diode bridge rectifier to our system, which transferred the AC power to DC power after the power was received by the secondary coil. Last, I focused on locating an AC 3-phase power source and installing a 3-phase power plug. Initially, I did research on multiple AC power supply options before I was able to locate a AC power source within the URI engineering professional shop. For our key acknowledgements, first of all, we would like to thank our technical directors, Mike Bronner and Robert Scala, for giving us their time and guidance by providing us information and aid in order to achieve the best possible outcome of our project. We would also like to thank our professor, Dr. Sunek, for putting together this capstone project with passion and urgency and inspiring us all, and for providing us with the wonderful opportunity to work with our sponsors, General Dynamics Electric Boat, on this project. Finally, we would like to thank Mike Smith, Jack Murphy, and Brendan Smurbeck for their help in assisting with the capstone program and for helping us with our project and our risk management setup, as well as Professor Jung, Sharav Raman, and David Ferreira for allowing us to use the electronics lab and providing us access to three-phase power.